Hello. In this video, I wanted to do a introduction and reasonable discussion of the feature set of QA40xPlot for folks who may have used it but would like to get good at it, and for people who want to know what it does. So let me go ahead and start. It is a simple audio test application that uses the QA402 or 403 audio analyzer. And there are a bunch of easy to run comprehensive tests. Harmonic distortion, intermod distortion, I won't read them, but I will go through each of the tests fairly quickly with some discussion. And the technology it's based on is C# and Windows. It runs Windows 10 or 11, and there's a very easy to use installer. The source is completely open on GitHub. Alright, and here's the application. Let me go ahead and get started. So at the top are a bunch of tabs, one per test. Each test has its own settings and its own display. So it's very easy. If you want to do an intermodulation distortion test, you go to intermodulation, you pick your test, and you run it. And then you get analysis specific to the application you're running. So it's pretty easy. Now, almost all of the tests, in fact, all of the tests have a chart. So let me discuss how to use the charting effectively before I get into each of the tests. And if you know this well, you can go ahead and just skip it. But let's take any of the charts. Let's start with scope because it's the most obvious. So here we have a blue and a red trace. Those are the left and the right channel. I can turn the right channel off. I can turn the left channel off. I can look at one or the other of them. And as I move the mouse, you'll notice I have a cursor on the right tracking the mouse movement. If I click, it stops tracking, and it tracks whichever channel I have showing. So here it's just simply time and voltage. For the chart, you can often bring up summary data, which is a little box showing more about the chart. You can bring up also tab info, which is for this tab, how it is described. Here it's a little busy. Let's get rid of some of that so you can see it better. All right, let's give the chart a name, something stupid like sample, and a heading. If we just click outside here, they will both take place, and now your chart has a little bit of discussion. Also, you can change the colors that are plotted. So let's take pink. All right, not a color you would normally use. And now right is red, and maybe we'll make right a blue. How's that? All right, so you can customize the chart colors, and you can customize the contents of the chart. Let's get rid of the tab info. You can make the lines thick or thin. You can show the data points, which here isn't much. All right, now you see me zooming in and out, so let's talk about that. So how do you move stuff around on here so you can see exactly the piece of the chart that you want to see? All right, if I take the mouse and I scroll the mouse wheel, we zoom in and out where the mouse wheel is. If I take the left button and I drag, it moves the chart around. You can see the scale down at the bottom moving. If I use the right mouse button, it does a zoom. So here I'm holding down the right mouse button and dragging. And you can do much the same thing in each of the axes. If I drag an axis, just the axis changes, which is a nice way to keep your data where it is. Or I can also do things here. Fit to all of the data. There's a lot of data here. Or I can just change that and look at the beginning of the chart, or maybe the first 500 milliseconds. Okay, so that's how you change time scales and move the data around and see various pieces of the chart. All right, so that's chart changing, as you will. All right, let's go ahead and do how the tests actually work. So this is the standard spectrum analysis test. Normally you run a sine wave, you get a tall peak, you get to see the distortion components. So here we're running at a kilohertz at 1/10 of a volt from the generator. Let me go ahead and start. And I am 3 averages. Let's cut that down to 1 average, so it's fairly noisy. So here in our summary data box, you can see that we're running actually at 1000.5 hertz because we have it center in an FFT bin, and we're reading it at 0.2 volts because I'm using a balanced output and input. So even though the generator is called 1/10 of a volt, we're actually receiving 2/10 of a volt for a gain of 6 dB. Now, if I stop temporarily, everything sits here and I can play with the chart. Let me bring up the right channel. And the right channel is actually at 1/10 of a volt and minus 20 dBV. Same frequency because the right channel is unbalanced. So here for my testing, I have a balanced left and an unbalanced right. Makes it easy to see various and sundry differences between the two. And if I turn off the right channel, we get rid of the data and we get rid of the overlay. So very straightforward. In addition, for any test, I can get a prior test that I've potentially saved. Let's take one called mine. So now I have my first test, and we'll show the left data there. So when you do a test, you can actually save the data for later. Or I can get rid of the save. I can save my current test here simply by this, and by default it has this very long name with the date and time. But so now if I change to like 100 hertz and maybe 1/4 of a volt and 192K, and let's go ahead and start running this. And let's only look at the right channel here. So here you can see that the frequency's gone down, the amplitude has gone up, and of course it's a completely different chart. Stop. Now if I load my last test, well first let's get the last test. So that brings it up over here where I can look at it in the background. Here's the test we ran, and if you don't want to see it, you don't have to. Or I can load the test, and if I do that, it will become, not only will it show the current test, but it will change all of the settings back to what they were when I ran the test. So you know exactly what settings you used to create the plot that you're looking at. All right, now how do we run this specific test? Let's go through the details of this test. So to begin with, I am auto-ranging the test. The attenuator is really nice to make sure you don't get a voltage overload, but if, for example, I run at 42, what you're going to see is that the noise level goes way up. Oh, let me turn off auto-ranging and do that again at 42. And I'm going to actually show data in nanovolts and microvolts, so this is obvious. All right, so at 42 dB attenuation, we're at 131 microvolts for our noise floor. And the distortion is way below that because I'm just running a loop back. And then if I lower this to like 24, the noise will go down. If I lower it to 12, the noise will go down even further. Now the noise floor is only recalculated when we run the test, so note it's still at 130 microvolts. But if I now run this test at 0 and I click start, we will see the minimum possible noise for this testing setup, which is currently running at about 2.4 microvolts. So the lower the attenuation, the better the test results. Hence, it's often very good to just do auto ranging. And when you auto range, it will start at 42 dB. It will figure out the gain, and then it will take the least possible attenuation and the best possible noise result. And down here you can actually sort of watch it, or up here. So watch as I run. It starts at 42. It goes ahead and it does a test at 42 to figure out the gain, and then it sets the attenuator to 0. Because at a tenth of a volt we don't need any attenuation, and we have the best possible result, and sure enough our noise is at 2.4 microvolts. So running auto range takes a little bit longer for that first gain test, but gives you best possible results, and once you've done it, we can just now not bother auto ranging if we feel like it and run this test over and over again. However, I'll warn you, don't set the voltage way up when you do that, or you could overload. Alright, so let's run at 42 so we never overload to change other things about the test. First off, you can change how you look at your entries. So let's run at 125 millivolts, which should be 225 because I've got a gain of 2. But we can also look at other ways of viewing this. Instead of doing the generator voltage, if I do the device under test output voltage and I set it to 125 millivolts, it will go ahead and again calculate the gain and do the test. And now it's at 1/8 of a volt output, not input, and we're running the generator at 62.4 millivolts to achieve that output. You can also specify it as a power. So instead of that, let's say a tenth of a milliwatt's a little small. Let's say a tenth of a watt. Alright, if I want a tenth of a watt, then actually it's going to run the generator at 1/2 a volt, which is going to have it come in at 0.9 volts, which is a tenth of a watt. So you don't have to do any really exciting math. Our amplifier load is assumed at the moment to be 8 ohms, but that is changeable in settings. Alright, so that's just the attenuator, and this is consistent over many of the tests. And here's how we set the voltage, and then we can change the waveform, which I won't bother, and we can of course change the frequency. And for almost all of these you can pick a number, or you can go in here and type. So this is going to run at 225.3 approximately hertz at a tenth of a watt, and here it's 225.6. Alright, things which you can't edit have the standard combo boxes. Things which you can edit have editable boxes. So if we want to run, you can only pick between these 3 sample rates, these sample sizes. Let's go ahead and run now at 192.16. It'll run noticeably faster but lower resolution. And you can change the amount of averaging, which will reduce the available or visible noise. Let's change this, get the noise level down. And now we can actually start seeing the distortion. Let me go back to, say, 500 hertz. Alright. Now if you want to, by the way, fit to data, you can do that. If you'd like to view this in other than dBV, there are a lot of ways you can view this, and we'll see some later that are pretty interesting when we do things like distortion analysis. But for right now, it's running pretty well. If you want to see the distortion for each of the harmonics, it's right there. Or in percent, it's here. And we can also look at the markers and get a visual of what the distortion looks like. So as you can see, I'm on a balanced output, so the second and fourth harmonic are very, very low, but the third and the fifth are not. And you can, of course, see the same thing up here in the harmonic display. If I stop, I can again move the mouse around and view data points over here in the cursor. Or I can look at the right channel in the background. Okay, windowing. This is a really interesting way to see windowing, and it's useful. So let's do this. Let me zoom in here and zoom out here. There we go. And I'll just save both of these so that it doesn't move around on me. All right. We almost always recommend Han for your window, but here you can actually see what it'll do to a sine wave, and you can understand better. I'm going to just set it to 1/10 of a volt. All right, this is a Han window, but let's go through them. Some of them are pretty bad for a sine wave, like Bartlett. You would never want to use it for a sine wave, but for some other signals it might be good. Blackman isn't too bad. Now, flat top isn't too bad, but things like rectangular are really interesting for a sine wave. They give you the best amplitude output, but spread the noise all over the spectrum. So you'll notice rectangular has this elevated noise level, whereas Han has a much better non-elevated noise level, slightly less accuracy here perhaps. But this is the best all-around way to do it. And some of these are not bad, but many of them you would not want to use for a sine wave. Again, it depends on what your statistic you're most interested in. All right, I usually run it like 192K. It runs really well and it's very fast, so you can bump the FFT sizes and it's still moving right along. And often, if you set the averaging down to 1, there's often a fair amount of noise. And then increasing the averaging just reduces the visual noise. It doesn't actually change the signal. And the numbers you see up here are based on a single test, not on the averaged test. So what do we have up here? We're at 500 hertz at 2 volts. And now notice, by the way, if I mouse over the statistics, it shows what they are in the pop-outs, which makes it very easy to understand what's going on. All right, so there's the spectrum analysis and the distortion analysis. Let's move on. Intermodulation. Here's an intermodulation test that I've mocked up. It's not a standard, but it shows a lot of distortion, so it's convenient. If I start running this, we'll see all this stuff start moving. We have 2 here sine waves, one at 10 kilohertz, one at 11 kilohertz. Both of them are at a volt. And the output shows that one's at 10, one's at 11. The total voltage we're getting is 2.8, and it's just about a watt actually. Again, the gain is 6 dB because we're balanced. Noise level's not too bad. I'm running at 18 dB of attenuation. Now, one of the nice things you can do here is turn on the intermodulation distortion markers, kind of like the harmonic distortion markers, but only intermod. So it won't show the harmonics with little dots, but it will show all of the intermodulation spots. And here too, the intermodulation only is shown. So these are, you can look these up, but this is like 2F1 minus F2, 2F2 minus F1, and so on. And again, we can always look at the right channel if we're more interested in that. The lines can be thinned. We can turn off the data summary. We can turn the data summary, into microvolts instead of percent if we feel like it. And if you want a not custom test, most of the standard tests are right here. CCIF, which runs at 10 19 and 20 kilohertz, for example. And you'll notice when I pick a specific test, the things I can't change get grayed out. So the only thing you can change here is a voltage. So if we run it at 1/10 of a volt, the other oscillator, which is supposed to match for CCIF, also drops. And here they are. You can see this running in loopback. It has very little distortion, as you can imagine. What a great tester. All right, let's switch to scope. So let's, instead of chirp, let's like maybe use a sine wave. And we can't see anything here. There we go. All right, so here's a pretty typical sine wave. We're looking at the left and the right channel. If you want to overlap two sine waves, I can turn on the second generator. Now, interesting, you'll notice when I fit to data that there's some white space here and here. And the reason for that is that the harmonics are not entirely in sync. So if we look at all of the data, you'll notice there's an envelope. And that's why the total signal is actually 0.85, whereas if we only look at a little piece of it, it's not quite fitting. But all right, so the scope is very straightforward. It shows signal in, signal out in the time domain. All right, let's run a sweep. So this is a distortion versus frequency sweep with these settings. I can run one again. Let's go ahead and start. Maybe we'll change some of this. This is distortion versus frequency. Let's run, let's say all the way from 5 hertz to 50 kilohertz. Let's do 192K so we can get that kind of stuff. And let's do 1 step per octave because that'll take plenty of time anyway. All right, now as we run this test, it brings up little mini plots so you can watch the actual data being swept. And here's the test. And as I mouse around, the cursor shows me each data point and what the D values are for the data point. Now, I don't know about you, but personally when I'm looking at distortion, I'd rather view distortion as percent, and it can do that. Notice at 7 we're having a little bit of distortion, probably because of the input capacitance. But let's now, instead of looking at dBV for the distortion amount, let's look at percent. And let's get rid of the crappy data, honestly. All right, so now we can look at this in a percentage. And all of these will also look in percent. I can go, okay, at 1400 hertz, my total harmonic distortion is at 0.0002 because it is just loopback. And the noise level is very low. But you get this very nice summary and you ask, well, where's the right channel? Well, it's right there. And the right channel uses dotted data versus solid data. Again, here's your distortion in percent, or if you'd rather see it in dBV, here's your distortion in dBV for both left and right channel. If I switch to just the right channel, it will show it solid because it's more visible. And you can turn off the things you're not interested in, like some of the higher order distortions or the noise floor. If you just want to look at total, second, third, and let's even get rid of magnitude, here's the sweep, ignoring the low frequency sort of stutter. Really nice, really, really nice. The highest distortion is at 20 kilohertz and it's still not at 1E minus 3. All right, we can do the same testing for amplitude, and this one is a very interesting display. Remember, I'm running balance, so it's 2 to 1. Let's go ahead and start this. And this one will run from 1/10 of a volt to a volt from the generator. which of course is 0.2 of a volt to 2 volts from the balanced. Okay, but here we see distortion versus voltage. If I switch this to output voltage, sure enough, it goes 0.2 to 2. So that's what we're reading versus what we're sending. And then I can put it in power if I prefer. So if you want to run a test up to 100 watts, well, you can go ahead and type 100, and on a good-sized amplifier, it will run the amp at 100 watts. Hopefully you have a nice large resistor. Or we can just do it at voltage, and let's run, to a volt, or maybe if you prefer to see that in millivolts, 100 to 1,000. Number of steps per octave, test frequency we run at, the current amplifier load is settable here, so it's easy in your face. And of course the same sample kinds of settings. And if you're curious watching it run, let's do this one more time. And you'll notice right here, as it runs, it shows what the attenuation is and what the generator voltage is. And you'll note the attenuation actually goes up as we scan. So we're getting the least possible noise and the most accurate possible results without doing any work at all at each voltage level. Okay, last couple of tests. The response curve here, I am using a microphone compensation. It's just so that you see something interesting when in fact we're loop backing, so it's absolutely flat. And there are 3 different tests combined in the response test. You can do response, impedance, or just gain. And if you use gain, there is no microphone compensation and no reference impedance. If you do impedance, you set the reference impedance, which is connected between the right and the left channels, versus the impedance, which is connected between the left channel and ground. And for the most part, I'm not going to bother with these. And when we do run a test, we can either use a chirp, which you'll see running as a chirp, and it'll go tink. That was it. And indeed, it looks like we think. If we look at the right channel, it's going to be pretty much the same. Or we can look at other things like gain and stuff, but they're not going to show anything more interesting than this. You can turn off the chirp and have it run a sine wave. And we can do that. And now it's going to show you the little mini plots as it proceeds to do a more conventional test. And this is higher accuracy than the chirp. It is, of course, much slower, and it has many fewer data points to display, but each of those will give a more accurate result, and especially at low frequencies, chirp tends to be fairly inaccurate. So here you can see we only have now that finite number of test points, versus if I turn the chirp back on, we'll have a lot of test points very quickly. And we can change the sweep, start and end frequency, even using the chirp, and we have the same voltage sample rate, FFT selections as all the other plots. If you want to see that last mini plot, we can turn it on and keep them showing. At the moment, we did a chirp, so there are no mini plots. The last thing I want to talk about are random settings, as it were. At the top, there are 5 buttons. Help brings up help. Photo takes a picture of the current screen. Export lets you export data. So note, now I can export it, and if I do that, it will save it as an FRD file, which is a text file readable by apps like REW. I can save my configuration. I can load a saved configuration. Okay, so those are the buttons and settings themselves. You can change your app theme if you want it to be dark or light. Note that these themes are actually a bit better for touchscreens than what I normally run in, which is none, or classic, which is a little smaller, but whatever. You can change your amp load. You can say that there's an external gain block or attenuation block. Change some of the colors. Here, like screen colors, for example. Set the microphone compensation, power line frequency if you're overseas or outside the US. You can have it automatically save your settings on exit, which is kind of nice because it saves your window. It will automatically reset the attenuator to full on exit by default, which is safe, so things won't burn out that you're not expecting, and obvious other stuff. So that's about it.